What specific problem does the diffusion-guided language modeling (DGLM) method aim to solve in the realm of language generation?
The diffusion-guided language modeling (DGLM) method aims to address the challenge of effectively guiding language generation to meet specific attribute preferences without the drawbacks associated with traditional fine-tuning methods. Specifically, DGLM integrates the fluency of auto-regressive models with the flexibility of diffusion models, allowing for the generation of text that aligns with desired attributes, such as humor or low toxicity, without altering the model weights. This is achieved by using a diffusion network to generate continuous semantic proposals that act as soft prompts for a fluent auto-regressive decoder. The method also allows for easy adaptation to new attributes by simply training a lightweight classifier, thus avoiding the need for dedicated models for each unique application. Overall, DGLM enhances the controllability of language generation while maintaining high output quality and diversity.
How does the proposed DGLM method work? Illustrate the method step by step, from the generation of semantic proposals to the final text output.
The proposed diffusion-guided language modeling (DGLM) method operates through a structured process involving three main components: a diffusion network, a lightweight prompt generator, and a pre-trained auto-regressive decoder. First, given a textual prefix, the diffusion model generates a continuous semantic proposal of a possible continuation by sampling from the latent space of sentence T5, which captures high-level semantics. Next, this semantic proposal is processed by the prompt generator, which transforms the embedding into a soft prompt that guides the auto-regressive decoder. During this step, Gaussian noise is incorporated to enhance the robustness of the decoder against minor errors from the diffusion model. Finally, the auto-regressive decoder generates the final text output, aligning it with the semantic proposal while maintaining fluency and adhering to any specified conditions, such as toxicity or sentiment control.
Can you provide a simple example that demonstrates how DGLM generates text based on a given prefix? Walk us through the main steps of the algorithm using this example.
To illustrate how DGLM generates text based on a given prefix, let's consider the prefix "the future of technology is." The process begins with the diffusion network, which takes this prefix and generates a continuous semantic proposal for a possible continuation. This proposal is embedded using the sentence T5 encoder, resulting in a 768-dimensional vector that captures the high-level semantics of the continuation. Next, the lightweight prompt generator processes this embedding into a soft prompt, which is then fed into the pre-trained auto-regressive decoder. Finally, the decoder generates text that aligns with the semantic proposal while maintaining fluency, effectively producing a coherent continuation such as exciting and full of potential innovations. Throughout this process, Gaussian noise augmentation is applied to enhance the robustness of the generated text against minor errors from the diffusion model.
What are the key theoretical or practical advantages of using DGLM over traditional fine-tuning methods or other plug-and-play approaches?
The diffusion-guided language modeling (DGLM) framework offers several key advantages over traditional fine-tuning methods and other plug-and-play approaches. Firstly, DGLM decouples model training from attribute control, allowing for the addition of new attributes without the need for extensive retraining of the entire model. Only a simple logistic regression classifier needs to be trained. Secondly, DGLM effectively mitigates the decoding errors that often arise in plug-and-play methods by utilizing a diffusion model that can correct minor errors during the generative process, thus enhancing output quality. Additionally, DGLM demonstrates superior performance in controllable generation, outperforming existing plug-and-play methods across diverse benchmark datasets. Finally, the framework allows for flexible control over generation attributes while maintaining fluency and diversity, as evidenced by its ability to lower toxicity and adjust sentiment without sacrificing quality.
How was the DGLM method validated or tested within the study? Discuss the datasets, benchmarks, and metrics used for performance evaluation.
The DGLM method was validated using a subset of 10 million instances extracted from the C4 dataset for pre-training, which represents only 2.5% of the total C4 data. To evaluate its language generation capabilities, 5,000 random validation instances were drawn from both C4 and Open Web Text, conditioning the network on the first 32 tokens to generate a 32-token continuation. The performance was assessed using several metrics, including perplexity measured with the Olmo 1B language model, MAV scores for text generation similarity, and diversity metrics based on unique n-grams. Additionally, for toxicity mitigation experiments, the Jigsaw unintended bias dataset was used to train a logistic regression model, while sentiment control was evaluated using the Amazon Polarity and SST2 datasets. The results demonstrated that DGLM achieved lower perplexity, reduced toxicity, and higher diversity compared to all baseline methods, validating its effectiveness across various benchmarks.
What results were achieved by DGLM in terms of generation quality and control of attributes? Please be specific about metrics such as perplexity and MAV scores.
DGLM demonstrated strong performance in language generation, achieving lower perplexity and higher MAV scores compared to baseline models. Specifically, it matched or surpassed reference perplexity with sufficient classifier-free guidance strength, indicating improved fluency in generated text. Additionally, DGLM consistently produced more diverse generations than the auto-regressive baseline across both datasets, as evidenced by the diversity metrics reported. In terms of attribute control, DGLM effectively mitigated toxicity while maintaining fluency, achieving lower average maximum toxicity and toxicity rates than all baselines. Furthermore, it successfully adjusted sentiment in generated text without sacrificing fluency or diversity, showcasing its capability for compositional control when combining multiple attribute classifiers.